A UK energy executive picks up the phone. His boss is on the line and he's clearly stressed, demanding an immediate wire transfer. It's his boss's voice, all right. The tone, the pacing, the accent, all of it. Except it wasn't his boss. It was an AI-generated voice clone. And 200,000 was gone before anyone figured that out. That was 2019. Today, AI voice clones are sharper. And AI isn't powering one-off fraud anymore. It's reshaping the entire cybersecurity landscape from both sides of the fight. So how did we get here? In this video, we're tracing the history of AI and cybersecurity, from the earliest rule-based systems to the autonomous AI agents operating today. By the end, you'll see how AI changed what defenders could do in each era of cybersecurity and what attackers could exploit. Let's get into it. AI and cybersecurity didn't start with chatbots or deepfakes. It started with if-then statements. The first so-called AI in security was expert systems, programs that followed rules written by humans. Simple logic. If this condition is met, trigger that response. No learning, no adaptation, just a computer listening to instructions. Then, in 1986, something shifted. A computer scientist named Dorothy Denning published a paper at SRI International called an intrusion detection model. She proved that computers could do more than match known virus signatures, which are just digital fingerprints of malware we've already seen. Instead, they could monitor network activity and flag anomalies, things that looked unusual compared to normal expected behavior. That was a big deal. It introduced the idea that threats could be caught by spotting abnormal behavior, not just by recognizing attacks you already knew about. If you work in a SOC today, that concept is baked into practically every tool you use. Through the 1990s, AI research hit what's known as an AI winter. Funding dried up, interest faded, but the work didn't stop. Research in neural networks and Bayesian statistical methods pushed beyond rigid rule sets, and government programs like the DARPA Intrusion Detection Evaluation in 1998 created benchmark datasets to actually test what early prototypes could do. Those innovations, anomaly detection, heuristic malware scanning, early log correlation, became the foundation for SIEM, Security Information Event Management, platforms, and machine learning-driven security analytics in the 2000s. Many of them are still in use today. Coming up, machine learning breaks free from static rules and a whole new class of threats emerge. By the 2000s, machine learning changed the game. Instead of fixed rules, systems could now learn what normal looked like for a specific user, device, or application, and detect when something deviated from it. Think about what that means in a SOC. An employee who always logs in from California during business hours suddenly accessing systems from overseas at 3 a.m., that gets flagged. Not because it matches a known attack signature, but because it doesn't match that person's usual pattern. This is how defenders start catching what traditional tools missed: insider threats, stolen credentials, or breaches designed to stay under the radar. By the early 2010s, techniques like decision trees, clustering algorithms, and specialized anomaly detection let security tools model behavior dynamically. By 2015, that evolved into user and entity behavior analytics, UEBA, systems that watch for suspicious patterns the way a careful human analyst would. It shifted security from reactive to predictive. But as defenders started relying on machine learning, a new question emerged. What if attackers go after the AI models themselves? That's adversarial machine learning. Researchers discovered some serious vulnerabilities. Attackers could poison training data so a model learns the wrong behavior. Or they could craft inputs that trick a model into making confident mistakes. They could even infer whether specific records were used to train a model, which is a major privacy risk. And by querying a model repeatedly and analyzing the outputs, attackers could clone its behavior without ever even seeing the original code. The arms race between AI-powered defense and AI-targeted attacks was officially on. Defenders had smarter tools. But now those tools were targets. Then AI made a leap that changed the stakes entirely. In 2016, DARPA ran the Cyber Grand Challenge at DEF CON. AI systems competed to find software vulnerabilities, generate patches, and deploy fixes, all in real time, with no human intervention. They cut remediation time from weeks to minutes. It was remarkable for defense, but it also raised an uncomfortable question. If AI can autonomously find and fix vulnerabilities, it can also autonomously find and exploit them too. Then, in 2017, Google published the paper, Attention is All You Need. This introduced the transformer architecture, a new way for machines to process language by focusing on the most relevant parts of data and understanding long-range relationships. It was a research breakthrough. In hindsight, it planted the seed for every LLM, large language model, that followed. A year later, BERT arrived, bidirectional encoder representation from transformers. This is a model that could understand words in context, not just in isolation. For cybersecurity, that meant better detection of phishing patterns and more effective threat intelligence analysis. On the threat side, 2019 brought deepfakes and voice cloning out of the lab and into actual operations. Executive impersonation, financial fraud at scale, that phone call at the start of this video. On defense, UEBA matured and was integrated into SIEM platforms, centralizing and analyzing security data across an organization's systems. Using behavioral baselining, anomaly detection, and risk-based analytics, these tools helped analysts cut through alert noise and focus on what actually mattered. 4 years that cemented AI's central role in the cybersecurity landscape, and it was about to accelerate dramatically. Fast forward to November of 2022. ChatGPT launches. Generative AI goes from a niche developer tool to something anyone can access. The implications hit cybersecurity fast, on both sides. On offense, the barriers dropped. You no longer needed deep technical skills to write convincing phishing emails, generate code, or produce realistic-looking security reports. Organizations scrambled to update governance policies and tighten controls. Then 2023 showed what was really possible. Researchers at Highest Labs created Black Mamba, a proof of concept showing how a large language model could generate polymorphic malware. That's malware that rewrites its own code with every execution. No files to scan for, no traditional command and control infrastructure to detect. It slipped past endpoint detection response systems and exfiltrated credentials. The underground ecosystem moved fast. Dark web marketplaces started offering what they called malicious GPTs, tools like Fraud GPT and Worm GPT. Many had limited real capability. Some were repackaged open source models, others were simple prompt libraries. But their accessibility lowered the barrier for AI-driven cybercrime. This era also surfaced a new class of vulnerabilities, not in networks or endpoints, but in the AI models themselves. We've got prompt injection, tricking a model into ignoring its safety instructions. And there's tool call hijacking, redirecting a model's integrations to leak data or take unauthorized actions. OWASP published a dedicated top 10 for LLM applications to address exactly these risks. And by early 2024, researchers demonstrated that GPT could recreate functional exploits from detailed vulnerability descriptions, outperforming traditional scanners when given high-quality context. That's why rapid patching, careful disclosure, and strict input controls matter more now than ever. On defense, LLM-powered assistants started changing how analysts work. Unlike earlier ML tools that scored and clustered alerts, these could answer analyst queries in plain language, summarize logs, threat reports, correlate data, and draft investigation steps. Not just faster, but conversational and context-aware. Generative AI reshaped both sides of the fight, and now something even more autonomous is emerging. Which brings us to right now. Agentic AI. These are systems built on large language models that go beyond generating text or answering questions. They pursue specific goals through sequences of actions, autonomously calling external tools, APIs, and services. They can perceive their environment, make decisions, and adapt strategies in real time with limited or no human intervention. On the attack side, the picture is a little concerning. Think of it in 3 phases. 1. Preparation, probing for weaknesses, credentials, and tools. 2. Infiltration, breaking in, establishing backdoors, spreading, evading detection. 3. Execution, stealing data, disrupting services, spreading misinformation. Malicious AI agents could dynamically adjust their behavior to avoid detection, learning from failed attempts, modifying attack patterns, rotating through techniques to find what gets past defenses. That's a different type of threat. Not a script that runs the same way every time, a system that learns. Now, here's an important caveat. The full real-world effectiveness of malicious agents in actual operations remains uncertain, and there's a defensive angle here. When agents make API calls, install local models, or embed prompts into malware, those workflows leave traces. Traces your team can detect and respond to. On the defensive side, early agentic tools are starting to appear in security operations, blending conversational AI, research capabilities, and security telemetry to help analysts plan and execute threat hunts, compressing hours of preparation into minutes with a human in the loop for every decision that matters. That human in the loop model is going to be critical as these systems get more capable. The AI handles research and correlation, but the analyst stays in control. After tracing decades of evolution, if-then rules to autonomous agents, what should defenders actually take away? The technology keeps changing. Certain practices have held up across every era we just covered. 1. Identity is still your primary attack surface. So think strong authentication, least privilege access, regular reviews, MFA, even the most capable agentic AI systems relies on exploitable credentials and permissions to function. 2. Treat AI models and agents as untrusted systems. Isolate their access, validate their inputs and outputs, log their actions, and enforce policy in real time. Just because it's your AI doesn't mean it can't be manipulated. 3. Secure your AI supply chain. Vet the models, data sets, and dependencies you're using. Prioritize signed and provenance verified artifacts. Make sure you maintain software bills of materials that include AI components. 4. Patch quickly and limit exposure. The window between vulnerability disclosure and a working exploit is shrinking, especially now that LLMs can generate exploit code from detailed descriptions. 5. Stay aligned with evolving standards. Frameworks like NIST AI Risk Management Framework and the OWASP Gen AI Security Project exist for a reason. Learn about them and update your governance as regulations evolve. The bottom line: AI is now embedded in both defender workflows and adversary playbooks. Same playing field, both sides more capable. There's no single fix, but a well-engineered, multi-layered approach built on identity protection, least privilege monitoring, and current standards is what positions you to use AI as an advantage instead of a liability.